All right, moving into module 3.2.2. In this module, we'll be talking about sulfur, which is kind of nitrogen's counterpart. And I do these together because they're very similar in their, at least the cycles are very similar. And since we went over the nitrogen cycle, you'll understand and see the sulfur cycle a little bit better.
I'm not sure I understand.
All right, welcome to module 3.2.2. In this module, we'll be talking about sulfur and the transformations that sulfur undergoes. And so these sulfur transformations are very similar to the nitrogen transformations. And so I led with the nitrogen because it's the most difficult, it's the most complex, and everything after this, you can kind of compare to the nitrogen cycle and go, oh, these are the similarities and these are the differences. So sulfur is very important in our amino acids. So this is kind of where we get our amino acids. This is where we get our amino acids that we need, and for our growth, and animals as well, because animals are going to eat the plants that we grow in the soil. And so these amino acids are important for animal nutrition, and we eat the animals. If you eat animals, if not, when you eat vegetables, the amino acids that are made inside of just a plant material are important for our health as well. All right, so one of the main differences between nitrogen and sulfur is that sulfur is relatively immobile in the plant. And so remember that we talked about nitrogen will fill that plant up to the top. And then if there is a deficiency down below, or if there is a deficiency in the younger leaves, then we will send that nitrogen to those younger leaves. Well, that's not the case with sulfur. Once sulfur reaches its final destination, that's pretty much where it's staying. So the older leaves are going to get most of that sulfur first, and then the younger leaves are left to take up whatever may or may not be available in the soil. One of the clear-cut easiest things to see for sulfur deficiency is going to be interveinal chlorosis. Now, remember in nitrogen we had this deficiency in the older leaf, but in sulfur deficiency we're going to see this interveinal chlorosis, and we're going to see this happen on the younger leaves first. So a couple of the kind of important things that we're going to start seeing, and you'll start seeing this in your soil test reports, is going to be sulfur deficiency. And so it used to be back in Grandpa's day, they didn't have to worry about this because they were burning, fossil fuels, and all that sulfur was going into the atmosphere and making acid rain. So when it rained, we were getting a little bit of sulfur credit on top of that. So producers did not have to really apply sulfur. It was just kind of already added there when it rained. So they never really thought to apply sulfur fertilizers. Well, as we, started to try and clean up our environment, we had the Clean Air Act, and that Clean Air Act reduced those sulfur dioxide emissions by 50%. So you can imagine what that did to the acid rain, which is great because we don't want acid rain because it's destroying our forests, and it's got some other, it's destroying our waterways. So we reduced the amount of sulfur that was in the rain and the atmosphere, and we also reduced the amount of soil that was we reduced the amount of sulfur that was in the soil. And producers never really considered that because they never really saw sulfur deficiency. So what we're doing is we're starting to add low sulfur content to our basic fertilizers. And so we have ammonium sulfate. You'll see this as urea ammonium sulfate. And then also potassium sulfate is something that you might be starting to apply if you need some sulfur. These are three of your kind of sulfur sources in order to do that. So we had a reduction of this atmospheric sulfur. I don't know why I keep saying that. This atmospheric sulfur, and that reduced the amount of sulfur that was being replenished in the soil. Well, the crops are still taking up that sulfur. They still need it. So we're depleting our soil of sulfur faster than the rain can supply it. And so that's why we kind of have these sulfur deficiencies, whereas before we never used to have them. What's important to understand is that, this sulfur is also part of some of our parent materials. And so we are going to get some of that in our, just naturally from our soils, but that's not enough to supply the plant with what it needs in order to grow. So some of the things that are going to affect this sulfur adsorption, so sulfate. Sulfate is actually the plant available form. And this is going to be adsorbed to the AEC. And the different types of clay are actually going to affect that. And so it looks that it's kind of backwards. We would not expect sulfur adsorption to be greatest in kaolinite that has a low CEC. Or would we? Because if it has a low CEC, then maybe it has a high AEC, an anion exchange capacity. Maybe that's a good way to remember that. pH is going to influence that. And so, we didn't talk a lot about pH, but to understand pH, that when the soil is more acidic, we have a greater hydrogen concentration, or H+. And when the soil is more alkaline, we have a greater hydroxyl concentration, which is OH negative. And so if we have more H pluses and the overall net charge on sulfate is -2, well, then there's probably going to be more adsorption in that acidic soil. The more soil organic matter that we have, we're going to have greater adsorption. That's just, soil organic matter is important for CEC, anion exchange capacity, and water holding capacity. Those are the three big ones. Those are the three ones that we need the most of. So any of the nutrients that we talk about are going to be adsorbed to this organic matter. Doesn't really matter if it's sulfate or phosphorus or nitrogen. It could be boron. Any of the C. Hopkins Cafe managed by my cousin Mokul Nina are going to have some affinity for this organic matter. And then oxidation state. We don't really talk about oxidation state in here. That's a little bit more about soil chemistry and kind of what is the real charge on that sulfur. As I mentioned before, we have atmospheric sulfur that is, come from acid rain. We can have some dry deposition. So in that fossil fuel combustion process, they use lime in order to absorb some of that sulfur to that calcium. And not all of that is really captured. Some of that does make it up into the atmosphere. And it can be deposited as, very very minuscule particles that we probably don't see. Okay, so the fate of sulfur. We have deposition. We have plant uptake. Well, that's kind of the whole purpose of applying all of our fertilizers, plant uptake. There can be some volatilization, but not a whole lot. We can have immobilization and mineralization. With varying carbon to sulfur ratios, much like our carbon to nitrogen ratio. It can be adsorbed to the anion exchange capacity. or it can undergo leaching, or it can be leached. All right, so for our sulfur cycle, you'll see that this is much less, a lot less than our nitrogen cycle. So we had this deposition, whether it be atmospheric deposition or we apply some sort of fertilizer or manure, there's going to be sulfur in that. That is then going to eventually be as sulfate in the soil. That's the plant available form. And then plants will then take sulfate up. The whole purpose of applying fertilizers is for plant uptake. And some of this sulfate can be volatilized. It's a very small amount, just in general, because there are going to be some transformations that occur that this SO2 is volatile. So deposition, plant uptake, or volatilization. So in all of the cycles, we at least have these three transformations. Taken up by the plant, it can undergo immobilization, and it can be mineralized. So mineralization and immobilization, and that is where, remember this is the difference between, the transformations back and forth between organic and inorganic based on the needs of the microorganisms in the soil. It can be adsorbed to the AEC. Once it is adsorbed, it is likely to be taken up by the plant, or it can be leached. All right, so again, very similar processes. We're going to apply a fertilizer. It is going to undergo some transformations to be taken up by the plant. It will most likely, it's going to undergo immobilization and mineralization. It needs to be adsorbed to the soil somehow so the plant can take it up. And then eventually there is an anion of these, at least the nitrogen, the sulfur, and the phosphorus, that is subject to leaching. And this leaching is going to cause the environmental pollution that we're trying not to be a part of, right? That we're trying to minimize. So you need to understand what's going on in the soil and these transformations in order to minimize the impact, right? This is all about environmental stewardship and how we can stop polluting our waterways for the most part. So very dynamic, a lot of things going on. Very simple. Okay, so that brings us to the end of Module 3.2.2 for nitrogen and sulfur. You should be able to complete Quiz 3.2, which is going to ask you some questions about the nitrogen and the sulfur cycle and kind of some of the different things that we talked about. All right? We'll see you in the next module.